Hi everyone and welcome to the first of my advanced higher videos, and we're going to start in the course with the electromagnetic spectrum. Now, quite a lot of you, if you take higher physics, will probably find this section of the course quite reassuring because some of it will be things that you've done previously within physics. There are a couple of little things that you're going to need to look out for, mainly in terms of units as we go on. But I'll try and talk you through those as we kind of come to them. So having a look just at the slides just now, what we're really looking at just now is moving on to discuss elements of the EM spectrum. Now, some of you will maybe have done this in second year, previous in school, looking at different types of radiation. But what you have on here and what you'll see is that this is actually a very, very narrow kind of range. And the whole electromagnetic spectrum is made up of different waves. And those waves have different wavelengths, different frequencies, and they have different uses and different dangers associated with them. And what we can actually see in this is known as the visible region. And you can see from the middle of this slide that this section is tiny in comparison to the rest of the waves in there. So we're seeing visible light from red all the way through to violet, and out with that radiation still exists. It's just our eyes can't pick it up. So we're not seeing that, but we need to have an understanding of that radiation as well. So this is just a small cartoon just to show you these, also showing you these different wavelengths and things. This gives us an understanding of the electronic structure of atoms. If we have an idea of light that is perhaps absorbed or emitted from different chemicals, it gives us a really good bit of information about the electronic structure and things that we'll come on to later in the course. So we need to be able to understand what these waves are, their different properties, and what the different parts of them are. So you'll see here on the slides we have a diagram of the wavelength, and you can see the waveform as we go through. And we have this one wavelength, and what we're meaning by that is if you go from the peak or the trough or even halfway up, as you can see here, to the same point in the next peak within the wave, that is what we call one wavelength. And we give that this symbol here, lambda. Okay, so lambda just looking like that. Okay, that equals wavelength. For those of you that haven't done physics before. So that can be peak to peak, it could be trough to trough, it could be halfway to halfway. Now, the wavelength is the distance and it is measured in meters, or more commonly nanometers. And this is where we need to have an idea of our conversion. So one nanometer is the equivalent of 1 times 10 to the minus 9 meter. So if I have 1 nanometer, that equals 0.02. 1, 2, 3, 4, 5, 6, 7, 8. Is this right? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 1 times 10 to the minus 9. I needed to count all my zeros. It gets complicated. So that number of meters, that would be our nanometers right there. And you can look at this for scientific notation. If you've got your times 10 to the minus 9, all I've done is if I had my decimal point here, I've moved it 9 places and added zeros in. That's why I was doing all the counting, much like those waves. So that's where we get for our wavelength. Having another look here, we can see our frequency as well. Now, frequency is the number of wavelengths that pass a fixed point in a second. So if I have my waveform, okay, and the bigger the wavelength, I like to think the slower that wave is. So say in a second, I've started from here, I go to here, and that's going through. If I had a faster frequency, then I would be looking at these wavelengths being smaller. Those waves would be closer together. And I would have more waves passing through a point in a second. Now, frequency is given a symbol just of F for frequency, nice and easy to remember, and that is measured in hertz. Okay, that's measured in hertz, and hertz is equivalent to s to the minus 1 as well. So sometimes you'll see it written as s to the minus 1, sometimes you'll see it written as hertz. It's the same thing, okay? 2 different units for the exact same thing. That's our frequency. And then our velocity is quite easy in this stage. Velocity is a constant value. We are dealing with light, we are dealing with electromagnetic radiation, but we are dealing specifically with light, and that is a constant value. Now, physicists, you'll be used to using V in the equations that are coming up for this, but we use the letter C. I like to think of C as my constant, and C equals 3 times 10 to the 8 meters per second. Okay, and that is the speed of light. Okay, so those are the main things that I need to have a look at here. And having a look at the next slide, as I've already shown you, these high frequency, shorter wavelengths are, in terms of my visible region and anything out with that visible region, that's getting from the violet or purple end of my visible light and going out to my ultraviolet, up to my X-rays, and out to my gamma rays. If I have low frequency, long wavelengths, I like to think of those as being slow waves or moving slowly, and their waves are further apart. They are less damaging. You'll see that is down at the red end of my spectrum, and that comes down to infrared and down to the microwave and radio waves. So it's quite a good way for you to think about that, is that if you've got this high frequency, short wavelength, I think of them as being really fast and more dangerous almost, but they have higher energy. Okay, if you were to work out the energy of these, they'd be a high energy, these would be low energy. And these all relate in a nice wee triangle where we have, you'll see in the slide, C lambda F, and this is our first equation. So C equals F lambda. So speed of light equals the frequency times the wavelength. So if you know 2 of the 3, now you always know C, so if you know the wavelength or you know the frequency, then you're going to be able to work out the frequency or wavelength that you don't know within that. This is the relationship. Physicists, I'm pretty sure you'll know this as being a V in here instead of a C. It's the same equation, but we use a C. It should be in your data book, but we'll be using this and we'll be manipulating this later. As I've already said, this is just a really small part of the of the whole scale that we're looking at, of the electromagnetic spectrum, but this applies to everything out with the visible spectrum as well. So it doesn't just apply to visible light. This relationship will apply out with that scale as well. So if we have a wee look, there's one example on the slide here. It says calculate the frequency of red light with a wavelength of 690 nanometers. Now I'm going to do this on the page just now as well. I'll take a new sheet just to do this for us. So calculate the frequency of red light with a wavelength of 690. Now I like to, I'm a creature of habit when it comes to these, I like to lay things out and write down what I know. So I know that C equals 3 times 10 to the 8. And we are looking at a wavelength. So the frequency is what I'm trying to calculate. My wavelength is 690 nanometers. So 690 times 10 to the minus 9 meters. We have to convert this from nanometers into meters, because remember this was meters per second, wasn't it? So this is in meters. This must also be in meters. It cannot stay in nanometers. If you don't convert, you will not get the correct answer. And so then if I'm looking at, we know that C equals F lambda. I want to work out the frequency. And so if I do this, I'm going to have this C over lambda, because I'm going to divide by lambda on both sides. So then I'm going to have 3 times 10 to the 8 divided by 690 times 10 to the minus 9. And that's going to give me, we'll see on the slide here, 3 times 10 to the 8, that's going to give me 4.35 times 10 to the 14 hertz. And that would be the answer for that particular example. Second example that I'll put in here says a beam of light from a sodium street lamp is found to have a frequency of 5.04 times 10 to the 14 hertz. calculate the wavelength of this light to the nearest nanometer. So let's have a look again. I'm going to put C, I'm going to put F, I'm going to put lambda. C is a constant, 3 times 10 to the 8. And I'm being asked to calculate the wavelength, which I don't know. So my frequency is 5.04 times 10 to the 14. Looking at this again, I've got C equals F lambda. I want to work out lambda, so that's going to be C over F. 3 times 10 to the 8 divided by 5.04 times 10 to the 14. And that is going to give me 5.95 times 10 to the minus 7. Now that answer that you get from your calculator is going to be in meters. The question specifically asks you to put this into nanometers, and so in order to convert, remember we've got our 1 meter, 1 times 10 to the minus 9, that is going to equal 595 nanometers. Now I am obviously cheating just now because I have this on the slide next to me as I'm working it out rather than doing it on my calculator, but that's what we're looking at here. So be very, very careful. Remember that the wavelength that you get out of this equation you're going to have in meters, and we like these to be in nanometers when we're looking at it, because we're looking at such like wavelengths that are so tiny. So otherwise we're going to have really big numbers that we're going to constantly be rounding and it gets complicated. So we would like it to be in nanometers, specifically if the question asks us to do that. Okay. So moving on to the next slide, having a look at photons. Now, when we look at how things interact with electromagnetic radiation, it can be absorbed, it can be emitted by different substances, and it was noted that actually this almost behaves like a stream of particles, so almost like we have multiple particles being emitted rather than one continuous wave. And we call these particles photons. These photons contain a specific quantity of energy, and that specific quantity of energy, we would say that they are quantized. And this theory has given us a kind of second nature of light. So we say that it's dual natured. It can behave as a wave, it can behave as a stream of photons, little packets of energy. And if you have a look at this slide, these different circles here represent our different photons. And we would say that these photons all contain the same quantity of energy and that they are quantized. Now, here's a new equation for us to be able to actually calculate the energy that is carried by one of these photons. So in this case, we have E. E is equal to energy. My energy equals HF. Now, H is Planck's constant. Planck's constant you can find in your data book. There's a table in the data book that has some constants, including the speed of light. But Planck's constant, which I'll put over here, H equals 6.63 times 10 to the minus 34 joules seconds. Now, this is important. This part here, the fact that it's in joules is incredibly important because it means that we're going to have more converting to do later, which can be a bit of a pest. Okay, so energy, here, if I say my energy equals Planck's constant multiplied by the frequency. However, what we just put up onto the slide just now, it says it's more common to calculate the energy carried by 1 mole of photons. We want to look at 1 photon here. That's a very, very small quantity of energy. And if we're looking at this very, very small quantity of energy, it's not going to have much of an effect if it's just 1 photon, because you're getting more than 1 photon going through in a second. And you're absorbing way more than 1 photon of energy when we're talking about these calculations. So it is almost pointless for us to sit and just calculate 1 photon's worth of energy. Now, that's not to say that you're not going to come out with a question that will ask you to do exactly that. And if you want to know what 1 photon of energy is, then we will use E equals HF. But that's not particularly useful to us as a chemist. Ever since you've done National 5, we've discussed moles of substances, and that was because we were looking at one atom and one molecule was tiny. Looking at one atom, one molecule didn't really give us much because that was the tiniest amount of any chemical, and we used the expression of a mole in the same way that a dozen means 12. What you haven't covered and what used to be in the higher course is what the actual value of 1 mole is. So before we go any further in those slides, 1 mole equals 6.02 times 10 to the 23, I'll just say particles. So if I had 1 mole of hydrogen molecules, I'd have 6.02 times 10 to the 23 hydrogen molecules. If I had 1 mole of neon atoms, I would have 6.02 times 10 to the 23 particles. That is a massive number of particles, and it is a number that is tangible to us to be able to measure and to be able to see the effect of different things in chemistry. And the same thing applies. So what we want to look at is, instead of looking at the energy that is carried by 1 photon by itself, I want to look at the energy from 1 mole of those photons. We're going to do the same thing that we've done with everything throughout chemistry and make it something that is actually measurable to us. And so what I need to do, this number here, is called Avogadro's constant. You're going to be sick of constants by the end of this. So Avogadro's, oh, I can't spell today. We'll try that again. Avogadro's constant. Too busy talking. And so if I want to work out the energy for 1 mole of these photons, all I need to do is multiply by Avogadro's constant, which is this. We give that the symbol L, and if you have a look at those slides, that's exactly what we've done here, where L is Avogadro's constant at 6.02 times 10 to the 23. And this is what I would use to work out the energy. So far we've looked at the relationship between light, frequency and wavelength. We've then looked at how we can calculate energy from frequency and how we can calculate energy for 1 mole of those photons. The reason that I gave you C equals F lambda before is because what if I want to know the energy for 1 mole of photons, but I don't know the frequency? Instead, I know lambda, I know the wavelength. If I know that, then I can change this. Rearranging, looking over here, rearranging for F equals C over lambda. And so I can take this and I can change F. E equals LH, still there, so Avogadro, Planck, but instead of F is the equivalent of C over lambda. That shouldn't be a capital C, that should be a lowercase c. Okay, so E equals LHC over lambda, with this being a lowercase c. Ignore that bit. Okay. These are equivalent. These are the same thing. If I know the frequency, I'll use this. If I know the wavelength, then I'll do this. Same up here, if it's just for 1 photon in itself, that could be E equals H C over lambda, which I'll write E equals H C over lambda. That's the same. All I've done is I've changed F, because I know C because it's a constant, and if I know what my wavelength is, then I can use these. It can get reasonably complicated, but it's easier when you actually apply it to some questions. And it's about reading the questions and understanding what we're looking at here. So let's have a look at this example that I've got on the slide just now. It says, calculate the energy of 1 mole of photons of blue light discharged by a cadmium lamp. That's a lot of information. Calculate the energy of 1 mole of photons of blue light discharged by a cadmium lamp. Now, that is 1 mole of photons. That means I must be using Avogadro's constant. Now, what we just said, E equals LH, and in this case I'm going to use C over lambda, and the reason I'm going to use that is because if you have a look in your data book, you can find out the wavelength for blue light, or the wavelength specifically for cadmium. So if you look in there, it will tell you in a discharge lamp what that wavelength is. and we know here it is 480 nanometers. So if I put this in, Avogadro is 6.02 times 10 to the 23, multiplied by Planck's constant, which is 6.63 times 10 to the minus 34. And then I'm going to multiply that by another constant, 3 times 10 to the 8. Anytime you do this, you're going to have the same top line if you're using LHC over lambda. It's always going to be these three values. Dividing that by the wavelength, however, that wavelength has to be in meters. So we said that it was 480 nanometers from the data book, if you have a look in there. So 480 times 10 to the minus 9. And if we plug that into the calculator, and I have a look on the slide, you can see all those numbers have been put in here. That's going to give me a value, which looks ridiculous just now, 249,453. We never used numbers this big in chemistry before, so this gets confusing. This answer is in joules per mole. Now, physicists, you're going to be happy with that. It's in joules. As chemists, we're not very happy with that. We like using kilojoules. And so we would have to divide that by 1,000. So we would get 249.453 kilojoules per mole. Now, it's quite important, if you gave me this answer, okay, that's in joules per mole, if the question didn't specify the units, then that would be fine. Sometimes you'll find that the question specifies in kilojoules per mole, and if it specifies that, it is looking for you to be able to do this as well, to be able to divide by 1,000 to get me that into kilojoules per mole. The reason this is in joules per mole is, remember, Planck's constant has joules in its units, so it's not in kilojoules, it's in joules. And so that's where we get this from. You could substitute that 1,000 in, and I've put that in here in the slide as well. If it asks you to express the answer in kilojoules per mole, you can directly put that 1,000 as a denominator. I don't tend to do it that way. I like to just convert at the end. I keep it all the same, so I do this version, but some of you will have preferences in doing it in a slightly different way. This is another example looking at light-breaking bonds. So during higher, we looked at bond enthalpy, we looked at being able to break and make bonds. And what this question is saying is that the bond enthalpy is 159 kilojoules per mole. Calculate the energy in joules required to break one fluorine to fluorine bond. And this is us just having a look at Avogadro just now. Not so much looking at our light in this case, but I won't do this on the paper. All it's done here is saying that 1 mole is this number of joules, because it's 159 kilojoules, that should be a small k. And remember, 1 mole is this number of molecules, and that's the same energy. So 1 molecule, if I divide the energy by 6.02 by Avogadro, 6.02 times 10 to the 23, that will give me 1 molecule's energy to break 1 molecule. But then from that, we can say what wavelength of light would be required to break the above bond. So I know that the energy, I'm just going to block this off. I know that the energy in this case is 2.64 times 10 to the minus 19 joules. And that's to break 1 fluorine-fluorine bond for 1 molecule. It says what wavelength of light would be required to break the above bond. Now the relationship I know already between this is E equals LHC over lambda. Sorry, we're not using this. E equals HC over lambda because it's only for 1, it's not for a mole. It's easy for teachers to fall into the same trap as you. So E equals HC over lambda equals 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8. And I'm going to divide that by lambda. We don't know what that is, but we do know that this is 2.64 times 10 to the minus 19. Now, the energy it's given us is in joules, and we're happy with that because Planck's constant is. Okay, so that's, again, looking at those units, making sure they all correspond together. In order to rearrange that then, I'm going to have lambda equals 6.63 times 10 to the minus 34 multiplied by 3 times 10 to the 8. And I'm going to divide that by 2.64 times 10 to the minus 19. and that is going to give me an answer in meters, which is 7.53 times 10 to the minus 7, and that's in meters. So if I wanted nanometers, that's 753 nanometers, which we're happier with in chemistry. So that would be us looking at these different relationships and looking at the difference between using wavelength, between using frequency, between using 1 mole of our molecules or our species or chemicals, or just using one individual. There's a lot of conversions that go on in this, but with a lot of practice you'll find it's quite repetitive. We're always using Planck's constant and the speed of light. If we're using a mole of something, we're always using Avogadro's. It's only a couple of these values that actually change from question to question. It's just being able to decipher what's happening in here. So that's where I'll kind of leave that just now. There are other examples that you can go through. But moving on from this, we'll look at kind of spectroscopy and how that goes.